we are going to be jumping in. We're going to be talking about chapter 1. We got section 1. This is going to be all about system of linear equations and matrices. So I think you're going to find these first initial sections pretty easy. So just let me know if you guys have questions along the way. So we are going to be looking at, and I apologize, I have to keep it in this mode because this is going to allow me to actually draw on the slides if needs be. But we're going to be looking at an introduction to the system of linear equations, and then we're going to get into Gaussian elimination. So we're going to look at sections 1.1 and 1.2. So the objective of this first section 1.1 is that it's important to understand what are our systems of linear equations. And so we want to get some basic terminology out of the way, and we want to see, okay, how are we going to actually solve these systems of equations? So I think that this is probably pretty familiar for you all. You have some of your different parts of equations. You have certainly your variables. Here it's x. You have your coefficients for your variables. You're going to have operators. You're going to have your different constants. So just kind of remind yourselves of these different parts of an equation. You'll see them also in general formation. So here you have ax minus b equals c. So that'd be an example of replacing them with their nomenclature, basic general nomenclature. So here's my question for you, because this is what everything is based upon. We're obviously going to be dealing with linear equations, linear systems. So we're going to be on the same page. And I have to ask the question, what is a linear equation? Would this qualify as a linear equation? What do you guys think? No, or who says yes? Anybody say yes? Anybody who says no? Everybody else. So why is it no? Yeah.
Because it's y squared.
Yeah, it's y squared. We have the y to a power of 2. So that will not be linear. This has been raised to a power. So that one right there, y squared. That's going to cancel that from being a linear equation. What about this one? What's wrong with this one? Yeah, we got a sine x here. We got a trigonometric function. That's not going to work. That is not going to be a linear equation. What about this one? Who says yes? Who says no? Why is it no? Yeah, we got the x, y. We actually have a product of variables. So that is not going to be a linear equation. So if I asked you to tell me what in the world is a linear equation, what might be something you would say? Yes.
Like the variables are like raised to like only 1 power.
Yeah, exactly. Do you think we're limited to the number of variables?
No.
No. But what about this one?
Yes.
Yeah. So this one's still a linear equation, even though it has this half here. So sometimes people get thrown off by the fractions. What about that one? No, you're taking a square root of that x1, right? What about this one? Yeah, that's looking pretty good. What's interesting about this one?
X, I guess, but they're still different variables.
Yeah, they're still different variables. So I had a little bit different nomenclature there. Anything else? Yeah, it's got equal to 0. So basically, the thing that you need to remember is that all variables will occur to the first power only. You see anything else? It is not going to be a linear equation. So you might come up with several different formats here. Okay, so here's another thing to kind of know about linear equations here is that you're going to have sometimes see them represented differently. So here in this first equation, you might be reporting all your variables in terms of x, but then they're going to have your subscripts. So you might have x1 and x2 is going to equal to some constant. You'll see here this one, because this is only in 2 variables, they've gone ahead and named them x and y, so you might see that. Depending on how many variables you end up getting, they might actually then have nomenclature for the coefficients before it. They might call it all A and then use subscripts for those. So just realize you might see it in a couple different forms. So here, other definition that you want to know is that there are 2 types of linear equations. You're going to have non-homogeneous linear equations. Those are where you're going to have them equal some sort of non-zero constant. Here you're going to have a homogeneous set of linear equations. This is where they are going to equal 0. So this is going to be an important definition here. So you have non-homogeneous and then you have homogeneous equations. So we call this, when we have more than one linear equation, we call them now a system of linear equations, or we call it a linear system. So this is going to be a finite set of linear equations. So like we talked about, x and y are going to be your unknown variables. So here in these ones below, which would be your unknown variables? x1, x2, and x3 for both of those equations. So you'll see those in different formats here. So this is going to be another way of representing your general linear system. You might have, you could have all the way up to m different equations in your system. You might have up to n different variables that you will need to solve for. So a lot of times you will see, because the systems can get quite large, you might see this kind of nomenclature where, like I said, A is going to represent your coefficients, B is going to be your constants that they equal. Then a lot of times they represent the variables in X's with the subscripts. So here you're going to see this A11. Can anybody guess what that subscript means? What would A11? And you notice the next one over is A12. Yeah. Oh, that's right. Hold on. So you got A1, that's in the A. So that first subscript, that's going to be the row it's in. Then that second subscript, that is going to be the variable that it's multiplying against, which happens to be also kind of its position there. So A is in the first row. It is also being multiplied times a variable here, 1. So you're going to see that kind of systematic nomenclature as well. So just some ways that they are writing this. So here, yes, you're going to see double subscripting of A, depending on how sophisticated this system is going to be. So like I said, the first subscript is the equation in which the coefficient occurs, and the second subscript indicates which unknown it multiplies. So here, then you will have, obviously, your set of solutions. So if you have a really simple set of equations here, you might designate them just X and Y. If you have a very simple system of equations here, they're just in the X and Y variables, what do you think you can kind of say about those? What do you think those equations represent? They're in 2 variables, X and Y. Yes. Yeah, they're lines. So here they've gone ahead and you will have your solution where X and Y equals 1 and negative 2. So depending on how many solutions you have, you might have S1 all the way through Sn. So when you are creating your solutions in this instance, you only have a paired n tuple because you have one for X and you have a solution for Y. So depending on how many solutions that you have, which correspond to your different variables, you could go quite up in numbers. And so you might have a 4n tuple, you might have a 5 tuple, a 6 tuple, depending on how many variables you're solving for. So they call them n tuples for however many solutions that you have. So if you have this system here of these 2 equations down below, but they have 3 variables, what's that going to be? Those are going to be planes then, right? So hopefully we'll get systems that simple, but not always, right? So it looks like Christopher, yeah, he got it right. He got, was lines for the other one. Ryer's got, yes, the correct thing where what our subscripts mean. So here, linear systems in 2 unknowns, they are going to arise in connection with an intersection of lines. So if you have 2 unknowns and you find the solutions, you have 2 unknowns, you could have an intersection of lines. So let's look at what that looks like. Or you might have something happen where possibly the lines are parallel. So if the lines are parallel, what do you think happens? You have 2, yes. So you could have lines that are homogeneous, but if they are parallel, do we have a solution to the system, do you think? No, we sure as heck don't. So as compared to this one you might have a solution that is just 1 point. So you have parallel lines, no solutions. You have them where they intersect and cross at just 1 point, you just have that one solution. Can anybody think of a third scenario? Yeah, so what's going to happen then? Yeah, you could have a case 3 where your linear systems, now the lines coincide, so now you have an infinite number of solutions. So just think, you have an intersection, so they intersect at only 1 point, or you have parallel lines where there's absolutely no solutions for that system, or then you have those lines, they're collinear, and now you have infinite number of solutions. So the, case 1 is they intersect 1 point only. So pretty simple stuff so far, but this is the basis of things that we're going to build here. So like I said, a linear system of 3 equations in 3 unknowns, that is going to be the graphs of planes. So here you might see them in this format. So here you can see they've kind of changed it up. They have their coefficients labeled A, B, and C. They have their constants labeled D. They did go ahead and use X, Y, and Z for their variables. So like I said, you might see it many different ways. All right, so if we're dealing with planes, so before we were dealing with lines because we only had two variables, right? So we had them parallel, we had they intersect at one point, or they were collinear and they had infinite number of solutions. So keep in mind that's a simple system, so that's only in two variables. We're talking about lines. Now we have three variables here. These are going to describe planes. So now all of a sudden it gets a little more complicated. So what do you think is happening in that first one? What do you think that picture means?
No solution.
Ooh, yeah, who was that?
Daniel in the online.
Awesome. Yes. So why is there no solution?
There's no intersection.
Yeah, there's no intersection. All those planes are parallel, right? What do you think about the next one? So think about, is that a solution of the entire system? No. What in the world is happening with this one? All three. So remember, you have a system, right? So it has to be a solution for however many equations that you have.
These are all no solutions.
Are they? What do you guys think? Do we know why? So what is happening in this one? What's that trying to tell us? What is that picture of that second one?
It looks like two planes intersect with one another plane. I don't know what that means about that.
So basically you have two parallel planes, and then one of the planes is going to be intersecting each of the parallel planes at a different point. So it's going to intersect this bottom plane here along that line, and it's intersecting the top parallel plane here. So you don't have a place where all three are intersecting, right? Does everybody kind of see that?
Yeah.
We can do it with paper if you want. If you can imagine. So I don't know, if you want to hold one? You get to hold one, that's gonna be your plane. Here's the parallel plane. So these are touching at any point in time, and then this plane is intersecting both of them at different spots. But there's not a solution for all three together at once. What do you think is happening on this one? There's no solution, right? You've got a weird situation where two of the planes are kind of crossing like this. So you take this piece of paper. So here's the bottom two are crossed, and then your other one is going to go through them at different points, but they're not all going to be hitting the same. So this one intersects this plane here, and then this plane going through intersects this other plane there. So you still don't have a common intersection between all three of them. What do you think is happening in that fourth scenario? Why in the world do we see only two? Yeah. So you have two planes.
Two
that are
coinciding planes.
Yeah, exactly. So you have two, these are corresponding planes, and then this one is parallel to them. Once again, there's not a solution for all three at the same time.
Would the middle two just be, you'd only be left with two equations that are unsolvable? Or
Yeah, so these two would be solvable together. This one couldn't be part of that system then, though, right?
would that be the same for the ones in the middle?
Yeah, like if you decided to change the system and you kept only the equations that had a solution, there'd have to be a reason why, though. But then you'd be changing your system, right?
Yeah.
But those same three don't work together. Yeah. So then what do we think is happening here? Yeah, so these have solutions. What is happening in that first one? Yeah, there is literally one point, because all the planes are perpendicular here. Look at that one point that they intersect at. What are they doing here? Yeah, they're all intersecting along one line. So if you can imagine, you're kind of, here you have one here and one here. So see how this entire line here, they would be intersecting at? What do you think is happening in that third one? Yeah, they're all sitting like this. And what do you think is happening in that last one? Yeah, so two are sitting on top of one another, they're coplanar, and then that one is like this. So then you have your solutions along that line. So could be a lot of different things that are happening with this particular system of equations.
You said there's only one solution for the second diagram, or
So wait, for this one right here?
the second one?
Yeah, so it's all along that line.
Okay, got it.
So however long.
The
Yes,
intersection is the line like in the second one. You'd say it's like infinitely many
along that line.
along that.
The planes or the coplanar, obviously a lot more. So in any case, You might see, so these are the different things. I really encourage you to definitely look at those pictures and kind of visualize them for yourselves. So here we come to an extremely important conclusion. So this is something you want to burn into your brain here. So if we are talking about linear systems in 2 or 3 unknowns, so that means lines or planes, so 2 or 3 unknowns, they were going to have 0, 1, or infinitely many solutions. There are no other possibilities. So you either got 0, 1, or infinites. It's not gonna be just 2 or 4. It's gonna be either 0, 1, or infinite many. So that's a very important rule here. Okay, so what do you guys think? This is going to be, here's going to be a linear system with 1 solution. So does anybody have any idea of what you might want to do in order to solve this?
Add the equations.
Yeah, you could add the equations. One thing that makes it easier to kind of, for people to think about is they like to cancel out variables. So one thing that you can kind of do is figure out how would you make one of your variables cancel out. So here you could either add them directly, you'd remove that y, or as the book would have you do it, you could multiply this first equation by -2 and add it to the second one. So if you had -2x plus 2x, that's going to give you 0x, right? And then you have -2 times -y, that's going to be 2y. What's that going to give you? And then -2 times 1 is -2 plus 6 is going to be what? 4? Is that what we got? So we got what? 3y equals 4? So y equals what? Yeah, we got 4 thirds. Then what? Yeah, so what do we get for x? Yeah, you plug it back in, and then what would you get? Yeah, which is going to be 7 thirds, right? So your solution for x and y here would be your 7 thirds and your 4 thirds. So that one in particular would have 1 solution. This one, they have given us the example of no solution. So what would you do here? Kind of do that same thing, right? You'd multiply -3 times the top line, add it to the next one. So if we did -3x plus 3x, that's going to give us 0x. Then we have -3y plus 3y is going to give us what? 0y, right? And then we have -3 times the 4. It's going to be -12 plus 6 is going to be what? -6, right? Does that equation even make sense? No. So this is something that we would call an inconsistent system here. Does not have a solution. Okay, so let's look at the next one here. Ooh, this one. What do you guys think about this one? You notice anything about this one?
You can divide it by 2. That's it.
The second one is what? It's basically the same exact equation, right? One just a multiple of the other. So it's not going to really matter. So in this case, your second equation is a multiple of the first. Whatever you plug in for x and y, it's going to be true for that second one. So in this case, you're actually going to have infinite number of solutions. Now, if you want to, you can go ahead and do the math. But those are going to be your couple different examples of what can happen. So here we had 1 solution. Here, when we went ahead and tried to solve for it, ended up being something that was ridiculous, where 0x plus 0y equals -6, not happening. It's going to be an inconsistent system here, so it's going to have no solutions. Here, that second equation was a multiple of the first. Therefore, if you did, like, say, if you did -4, times that first equation, it's just going to end up being the same as the second equation. Everything's going to end up being zeroed out. So that second equation is not going to really tell you much because it's going to boil down to the first equation anyway. So here you're going to have infinite number of solutions. So here is another example of that. How do you recognize this one? Yeah, it's the same deal. Even though you have more variables, right? Now you have x, y, and z. But you still notice the same thing again. both the second equation and the third equation are just different multiples of the first, right? So this one's going to be another example of infinitely many solutions. So that one's a good one there. Okay, so here is where you're going to learn one of the different types of matrices that you're going to want to recognize and know how to construct. So you will have a set of linear equations, and you might be asked to put them into an augmented matrix. So this is going to be one of your first methods that you're going to be able to use to solve for a set of linear equations. So you're going to want to know how to put them into an augmented matrix format. So here's where we get into the history where they're like, ooh, well, here we could use matrices to help us out. And we're in the history of things, they started doing this. So as you will notice, here, this is the format. So here you'll have m different numbers of linear equations. Here you're going to go out to n number of variables. And then these equations are going to be equal to your constant speeds. So how you form your augmented matrix, can anybody guess what is happening? What are they just doing? Yes. Yep. Mm-hmm. So you can kind of pretend like there's a little equal sign in here, right? So this is going to be this first column. This is going to be the coefficients associated with your first variable. These are going to be the coefficients that are associated with your second variable, and so on and so forth, all the way through your nth variable. And then here is going to be whatever your b values are. So that is how you're going to form your augmented matrix. Now, keep in mind, here's where you got to remember the terminology. It's called augmented because it's also including the b on the other side of the equal sign. Not all matrices that we're going to work with are going to do that. So this is a particular type of matrix where you're including all the coefficients and the values for b. So does everybody kind of see that? So then when we go ahead and form our augmented matrix, how would we do this? So how would we take, first of all, this is going to be a set of planes, but how would we convert this into an augmented matrix? Okay. So I heard someone say 1, and then you said what again? So is that as a row or a column? Okay, so a row. So you're going to go across. For that first equation is going to go in here. So we got 1, 1, 2, 9. Then what's the next row? Yeah, 2, 4. What's? Yeah, this one's going to be -3, and this one's going to be 1. And then what do we got? 3, 6. What's this one? Yeah, -5 and 0, right? So that would be your augmented matrix for this set of linear equations. So keep that in mind. Ooh, so here is where, so if you look, does anybody have their books with them? So now we're actually going to be doing some stuff with these matrices here. So make sure that you're looking at possibly example number 6. Yes, so you're correct, Alvaro. We're just using the coefficients and the constants on the other side of the equal sign. So keep in mind, this is your first definition here. Besides what a linear equation is, now you have an augmented matrix. So some things that you're going to want to know that we're going to be able to do with these matrices, these augmented matrices, is we are now going to be doing some things that we call elementary row operations. Has anybody ever done this before? Yeah, so what context have you guys done these in?
What is this?
So now we have that matrice. So let's look at what we had before. So here, this would be an example of an augmented matrix that we have created. So now we're going to be looking at, okay, what are some different operations that we're allowed to do to it? So this is what is included on row operations. So that means across the row. You have your augmented matrix. So across the row, this is things you can do. So you can multiply a row through by a non-zero constant. That is going to be important that you note that it is a non-zero constant. Why would you not want to include 0? Because that's not going to tell you anything. That's not going to help you, right? You're going to eliminate that particular row, and that would not be good. Another thing that you're allowed to do within that augmented matrix is you can interchange 2 rows. So that's something else you're allowed to do. Or we are already kind of doing it, but you can multiply a constant times a row and then add that row to another row. So that is going to be your other operation that you're going to want to be aware of. So definitely look at these elementary row operations. You're going to want to kind of commit these to memory, make things easier on you. So we will look at example 6. So we're going to actually do some elementary row operations on here. So how would we, first off, how would we create this augmented matrix? Who wants to call that out? So we got 1, 1, 2, 9. We got 2, 4, -3, 1, right? Then we got 3, 6, -5, 0. So here we're starting off with our augmented matrix. So then if I told you, what if the first thing that we are allowed to do is going to be add -2 times the first equation to the second. So you're going to add 2 times the first row to the second row. What would that look like? So if we're going to do -2 times the first row, yeah, so if you wanted to, you're going to want to think about how are you going to get rid of some of these numbers and simplify it down. So they're asking us to do -2 times that first row and add it to the second. So here, what that would mean, here you have -2 times 1, that's going to be -2. Plus the second, what would that give you? Yeah, it's going to give you 0. So you got -2 times 1 plus 4 is going to give you what? 2. Okay, then we got -2 times 2. It's going to be -4 plus -3. Okay, we got -7. Then we got -2 times 9. It's -18 plus 1 is going to be what? -17. So we left that first row alone. And then we have this as our next step. So that's kind of interesting there. Now, the next thing that they want you to do is they want you to multiply -3 times that first row and add it to the third row. So what would that give you? So if you had -3 times that first row, add it to the third row.
Question, you say like -3, like where are you getting that -3 from?
Yeah, so we're going to get into what that means later. They're just leading you through an example of elementary row operations, but I love your question because they haven't told you yet why you're doing it that way. But there is a reason, so I like that you're thinking. So be noticing what happens to the matrix upon these operations. So the next one, yeah, we do -3 times that first row, and then you add it to the third. So we got 0 at the bottom. We got 3 minus 11. And we got -3 times 9. So we got -27. Okay, so our next matrix is going to be this. So I do like to stop right here and make sure, does everybody see where those numbers come from? Because you're going to have to be able to do this. So if you don't see where they came from.
I have a question.
Yeah.
They want to convert the low bar to 0, or they want the diagonal one, or what they want.
Yeah, exactly. Does anybody notice one thing that's happened?
Yeah, we're doing like the corner left.
Yeah, what do we do? We're starting to create zeros. We're starting to make this what we call a leading one. So-
Keep it on the top row, like when you're multiplying like the -3 and the -2, or could you apply that to the second row? And then
Yeah, so in the future, you're going to be kind of looking at these things strategically because you are allowed to interchange rows, right? So we're doing some matrix operations right now. We're not really understanding why we're doing it, but you'll realize in the future that you actually want to be very strategic about it. So for instance, on your original matrix, the reason why they started off with the ones for that row, they left that top row alone, is already have the first number as 1. If for some reason that top row was in a different position, maybe you might want to bring it up to the top. So it already starts with a 1. So you're going to want to think about being strategic in this. Okay, so yes. Ah, yes. What is one of the things you can do? I like that question. What row would you do? What if none of them started with a 1? Which one of these could you use? You could use this. Yeah, so if none of your rows had started with a 1, let's suppose all of your rows started with a 3. How would you get them to a 1? You multiply 3 by 1/3. So just realize you're going to have to think creatively and kind of manipulate these things. So just realize, that's why I said, you're gonna want to remember these, or at least bookmark them, right? Put them on your study guides so you remember what you can do. So getting back to our matrix, let's see where we're at with this example. Okay, so we're at the, all right, we'll go to the next page here. So we were at 1, 1, 2, 9. We're at 0, 0, 2, 3. Sorry, my handwriting on. We had -7.
I have a quick question.
Yeah, go ahead.
Is this for the gas elimination or something?
Yes, this is going to lead into your Gaussian. Yes, you're absolutely correct.
Okay,
Good
thank you.
reading. Yes.
Pick the number -2 initially to multiply by because that's what's creates the first 0. I guess.
Mhm. Yeah. So you guys are also taking note of these patterns you're already seeing. Okay, so our next step is going to be multiply the second equation by a half. So we're going to multiply this second equation by a half. What's that going to do for us?
The 2 is gonna have 0.
If we're multiplying the second row by a half, what's that going to give us? 0, 1, -7 halves, and then -17 halves, right? And then we have 0, 3, -11, -27. Just to show you what's starting to happen. Ooh, we have a leading one here. Now this one here is starting to look pretty good. What do you think they might suggest we do next? Gotta get rid of that 3. What do we want it to be? We do want it to be a 0. So what would you guys recommend we do?
Multiply the second one by the
Why would you not choose the first row?
multiply by the first one, 3 is gonna be again.
Yeah. If you use this first equation, you did -3 times it, well, then you're starting to put a value here in this first spot again. You don't want that. So you want to make sure you pick this second equation where there's already a 0 here. So it doesn't matter if -3 is multiplied by it. It's going to remain that 0. And so it doesn't add anything to that third row. Okay, so if we did, sorry, I'm kind of doing these in an interesting way here. So if we did -3 times that second row and added it to the third, what would that resulting matrix be? So first one, yeah, definitely. First one obviously is going to stay the same. And okay, we got -3 times 0 plus 0. That's going to give us 0, right? Then we've got -3 times 1 is -3 plus 3. That's going to give us a 0. We got -3 times -7 halves. So that's going to be, what, 21 halves minus 11. Anybody do some math on that? I think, what is that going to be, a half left over? Let's check what we got. -1/2. All right, we got, so let me fill in the rest of these. We got -17 halves. Then we got -3 times -17 halves minus 27. You guys can cheat and look in the book. What did they get for that? Anybody have theirs? Or they can do that? Yeah, -3 halves. So now we're looking kind of pretty. What do you think you might do next? Whoop, oh, yeah, question. Let's see, because you're trying to get this to be a 0. If you multiply this third row by 1/3, this would become a 1. Yeah.
So is there like a pattern with like U24 ones?
Yes. So I haven't told you the pattern yet, but they decided to kind of show you the different types of elementary row operations that you can do in this example. But if you're kind of watching how this progresses, you start to notice some patterns. We're going to go into that in the next section. Like, why are they doing it this way? Okay. So then we're almost there, folks. So we've got, let's go ahead and get this one in here. So we've got we got 1, 1, we're almost there. 2, 9. We've got 0, 1, -7 halves, minus 17 halves. Then we've got 0, 0, -1/2, and then we've got -3 halves. These are now our augmented matrix now is looking like this. Now they're going to want to do what? They're going to multiply which one? The third one? So what would you multiply it by? Yep. So you're going to multiply that last one by -2. So you've got 1, 0, 0, 1, 1, 0. We've got 2, 9, -7 halves, -17 halves. Now you have 1 here. What would that last one be? 3? Okay. So we've got that now. Now what's 2 other operations that are left, do you think?
Could you multiply the third one again by -2?
The third one by -2.
Then the top minus 1,000.
So in the book, they have that you do -1 times this second equation, and you add it to the first. Can anybody think what they're trying to achieve with that?
They try to get 0, buildings.
So if you did -1
Cancel.
times this second row and you added it to the first, you're trying to get a 0 in this spot.
So you.
I don't expect you to know why yet. They are getting really ahead of themselves in this example, just to make you aware.
So once you multiply it, well, you can add or subtract it to either row.
Yeah, so you want to go down all the way down the matrix C, and then what we're going to be doing is we're going back up.
Oh.
And you're going to be figuring out why we're doing that. But they decided to introduce all this stuff in this example ahead of time. So that's what they did. They did -1 times that second equation. They added it to the first. And then they added 11/2 times the third equation to the first. And so just to let you know, all at the end of the day, they were able to get to this augmented matrix. So I did want to get to this last matrix because I wanted to show you what that will lead to. I did decide to skip. So I skipped steps to get to the last matrix, but you can do it for yourself. So you basically add -1 times the second equation, you added it to the first. Then they would add 11/2 times the third equation, and then they added it to the first. And so what they ended up with was this final augmented matrix. So if you were to look at this final augmented matrix, because basically this is going to set the stage for the whole next section, you would say this is a pretty cool, simplified looking matrix, right? Why is it so nice and pretty? And now that we have this particular resulting augmented matrix, how does it relate back to the equations in the first place? Yeah.
We have like x equal 1, y equal 2, and z equal 3.
Yep, you got it. So now what are our equations now? Now if we were to put this back into equation form, we would literally have 1x plus 0y plus 0z equals 1. So that's going to be for that top row. Then we'd have 0x plus 1y plus 0z equals 2. So that's for this next row. Then we'd have 0x plus 0y plus 1z equals 3. And then you simplify that even further, and we have x equals 1, we have y equals 2, we have z equals 3. And you have found your one solution to that system. So they didn't explain to you why you're doing all of this. They're just introducing you to elementary row operations, but hopefully they're hoping by the time you get to the end of this example, maybe some light bulbs start going off, and you see, oh, there was a rhyme and reason to doing these elementary row operations, because now we've simplified these things to where now we actually can find out what are going to be the solutions or values to our variables. So what do you think about that? So that is where we are headed. We are going to be using tools at our disposal with matrices to find these solutions.